We're going to look at section 3.2, measures of variation. And I just want to start off with having you find the mean for each of the data sets that we have. We have McDonald's chicken sandwiches, total calories in each sandwich. And we have McDonald's hamburgers, total calories in each sandwich. Down at the bottom there, you do see a mu. The mu is for population mean. I'm looking at the chicken sandwiches as being a population because I have every chicken sandwich off their menu. And then I'm looking at the hamburgers as being a population because I have every hamburger off the menu. I didn't take a sample of each type of sandwich. I took all of them, so I have two populations up there. So do just a quick little refresher, make sure we can find the mean of a data set. All right, we should come up with 490 for our chicken sandwiches. And for our hamburgers, should come up with 455. Just continuing to get used to the symbols, guys. The mu, population, mean. Just to continue getting used to the symbols. We're going to look at some formulas that look kind of big and scary today. But once you know what the symbols mean, the computation piece is not very scary at all. So we will work through lots of those things today. So just a little start off with the symbols there. The first measure of variation we have, we already worked with this unit. It's your range. The range, though, is symbolized. We really never talked symbol for the range. It is a capital R. And simply highest value minus lowest value. So for chicken sandwiches, we can take 630, which was our highest, minus 360, and we get our range of 270. Now if we do the same thing for hamburgers, the range comes out to be 490. So if I just go based on the range, I would have to say that the hamburger data is more spread out, that it's more variable than the chicken data. However, here's the problem with looking at the range as a measure of variation. If you have an outlier, so a super high value compared to the rest or a super low value compared to the rest, it can greatly affect the range. So if we look at our hamburger data, our highest value was 740. If we get rid of that really high calorie burger, the range is knocked down to 290. Now the range is really close to the range for the chicken sandwiches. So one high value can greatly affect that measure of variation. So it's not all that widely used. What is more so used is what we're going to look at next. Data variation is based on the difference or distance each data value is from the mean. That difference or distance, you can look at it either way, is called a deviation. To take a look at our variation, we have our population variance. The population variance is the average of the squares of the distance each value is from the mean. Now I know you're thinking, Miss Golly, why would we square those things? What happens when you go to find each individual distance between each data value and the mean, if you add all of those up to try to find the average, the total always equals 0. If I have a sum of 0, that's not going to help me find an average very easily. And it will happen with any data set you try. If you just take each data value and subtract the mean to find that difference or that distance, if you add those all up to try to find the average, you're going to get a 0. So to get rid of that 0 idea, we square all of the values to get rid of any negative differences that we have. So if we get rid of the negative differences, we will get just a positive number. We won't get 0. So that's why we have to do the squared piece first. Then to now make our units match, we find what's called the population standard deviation. And it's not really something extra to find. The only thing you have to do is take the square root of your variance. So if you go through the work to find the variance, you're going to have whatever your units are, the result will be units squared. So to fix that and to get our units just back to plain old units, whatever they are, we take the square root. So that's the only difference, population variance, population standard deviation. We have to do the variance, we have to square those distances, so we get rid of that sum of 0. And then to get our units to then again match, to get away from units squared, we take the square root to find the standard deviation. So that's how those two things are connected. They're very, very closely related for us. So let's dig in and let's find our variance and standard deviation. And again, the standard deviation is going to give us that average distance that each data value is away from the mean. So it's going to tell us how spread out our data values are from our mean. Is the mean a good representation? Are they pretty close to the mean? Or are our values more spread out and our mean is not a good representation of our data set? That's what we're looking for. So I just want to do this. I want to keep our data set small because the computations can get tedious if you have a large data set. So I'm just going to stick with the chicken sandwiches. And these are, again, I'm just pulling these from the chicken sandwich data. So our values are 360, 420, 530, another 530, 630, 470, 580, and 400. Again, these are just the chicken sandwich values that we started with finding the mean for. And again, we're trying to figure out the distance, the average distance each data value is from the mean. So in order to do that, we have to first start by finding that actual distance between each data value and the mean that we found. Whenever you see the capital X, you guys saw this when we were finding the means last section, this capital X just represents your actual data values, those raw data values. That's what the capital X will represent all the time. The mu, remember, is our population mean. So we take each value minus the mean, and for chicken sandwiches we found that to be 490. And you want to make sure you keep it consistent. It's always value minus mean. You will get some negatives. You absolutely will get some negatives. So it depends if that value is higher or lower than the mean. So you will get some negative values, you will get some positive values, and that's okay. Don't change the order of anything, don't try to make them all positive. We will fix that with the squaring. Now maybe for the first few guys, I would write out the steps, just so when you look back as a reference in your notes, you don't just wonder, well wait, why do I have negative 130? Maybe write how you got that, just for the first couple. And then from there on out, let the calculator do the busy work. I wouldn't write those all out. Or if you want, you can write down what I have and trust that I did the subtraction right. Now, if you don't believe me, I said we had to square these distances or differences because if we add them all up to try to find the average, we get a 0. If you do add all these values together, if you want to pop them in your calculator and double check me, you're more than welcome to. If you put all these distances in, it always comes out to be 0. You're always going to have some values above your mean, some values below the mean. You add up those differences, you're going to get a 0. So if I'm trying to find the average distance or difference, a 0 doesn't do me a lot of good. It doesn't do me a lot of good at all. So that's where the squaring piece comes in. We have to square that difference. Don't do any extra work. Don't do the subtracting again. You already did that. So take your difference and square it. Don't do all that extra work again to then subtract and then square. Now, if you want to shortcut it, again, I'm doing piece by piece because this is your first time seeing this. what you could do is literally put in your calculator 360 minus 490, put that in parentheses, put the squared on the outside, hit enter, you'll get the 16,900. Try to cut out as much of the busy work as you can. I'm laying it out for you step by step today. Find your own little shortcuts. Find your own shortcuts. I'm not expecting, when I ask you to find variance and standard deviation, that you give me this elaborate table every time. I'm showing you how to get the different pieces. You shortcut as much as you need. Let the calculator do as much of the busy work as you possibly can. Please, please, please. So believe it or not, we do have all the pieces we need to now fill in our formula. Now I know, I'm being very honest, when I first took stats and I saw my first formula with all the symbols, with all the Greek letters in them, I said, whoa, wait a minute, what's going on? This looks tough. Once you get used to the symbols, though, it doesn't become so bad. The first symbol we want to look at is the symbol that actually represents population variance. That is a lowercase sigma, and because it's variance, it's going to be squared. And the squared is there because we had to square those differences. We saw capital sigma a few times yesterday. And we know that that means sum. It means we have to, put a little plus sign there, means we have to add all those, whatever's after it together. In this case, it's differences. Notice this piece that comes after the sigma, the piece that comes after the sigma matches our last column. We've already done that. We just now need to add them all together. We just need to add them all together. It's all we have to do. That's all we have to do is add them together. There's no extra work. So something that might look a little scary or a little different to start with, all that numerator means is we take each value minus the mean, we square it, and we add them all together. So something that looks a little complicated, the computation is actually very easy for it. So that's my numerator. That's my numerator. The capital N is just your population size. That's all the capital N is. Population size, simply how many data values are there in your population, or how many objects are in your population. And in this case, we have 8. We do a little division, 7,650. Now again, this is the average squared distance that each value is from our mean in the data set. 7,650, we don't even have a single sandwich it's that high. That's where the standard deviation comes in. Standard deviation, folks, all you're doing, literally, is taking the square root of your variance. That's all you're doing. Square root of your variance. Our rounding rule. Little refresher from yesterday. I know we talked about the rounding rule yesterday. We go to one more place value than the actual data itself. So my actual data is to the ones place value. So when I do variance, standard deviation, if I wanted to find the mean, I go to the nearest tenths. If I have to round, I go to the nearest tenths. Now, if you turn the page, we've talked in here a few times that it's not always convenient to actually get all the data from the population. Sometimes it's not convenient, sometimes it's just plain impossible to do. So when that happens, we end up with a sample. The formula for sample variance and sample standard deviation are just slightly different. The variables are slightly different because we're talking sample versus population. So let's start there. Remember, for your samples, you're just using those Roman letters. So literally, when you see S squared, it is just an S. There's no fancy name for it. It's S. That's all it is. Your X bar, literally read as X bar, remember that's your sample mean. And yes, will you need to know symbols? Yes, you're going to need to know symbols. So you know what to actually put in the formulas. Got to get used to the symbols. I know it's different for a lot of us. A lot of different symbols. Then the next different symbol, now instead of a capital N, we have a lowercase n. And that just represents our sample size. Or in other words, how many data values are actually in our population. That's all we're going for with that. Again, the only difference between sample variance and sample standard deviation, we're taking the square root of the variance. It's the only difference. We need to get our units back to plain units and not units squared. Sample variance, can use it to estimate our population variance. Same with standard deviation. Now, one of the differences, though, between the two besides the symbols is the denominator. With the population, we just had capital N, just population size in the denominator. Now, with samples, we need to do an N-1. Research had been done to compare population variance versus the sample variance to make them more agreeable, to make the sample one more unbiased, or excuse me, more unbiased. We have to do the N-1. It gives us a better estimate of the population variance. It gives us a better estimate. That's why it has to be done that way. There are some shortcut formulas, and sometimes I don't know how much of a shortcut they really are. Symbol-wise, I'm not going to go through and use both of these for our data, but I just want you to be aware what the symbols mean. For this piece right here, this means to square each data value then add them together. This piece means add all data values together then square the result. So two things that look very, very similar, but again, it's just getting used to the symbols and what they mean. Square each data value, then add together, versus add the data values together and then squaring the result. So just a little bit of a difference there. We've been working quite a bit with group data. We found the mean for group data in our last section, and we had a somewhat similar process for it. We can also, in turn, find the variance and standard deviation for group data. Starts off very similar. We have our classes, we have our frequencies. Very similar to finding the mean for group data. We go ahead and we find the midpoint for each class. Just a little refresher for you, the fast way to find the midpoint, take your class limits, add them together, and divide by 2. Again, maybe you just want to do that for the first one, just for the sake of notes. They make a little bit better resource if you can actually look back and know where the numbers actually came from, how we arrived at those. So go ahead and find your midpoints. And remember that difference should be consistent. So from 66 to 73, we had to add 7. So to get the next midpoint, we'd add 7, add 7, add 7, add 7. So remember, you can quicken that up a little bit. The difference between the midpoints should be equal. Now, just like finding the mean for group data, our next step is to take each frequency times that midpoint. Again, for the first one, I would probably write out how I actually came up with 198. Maybe even for a second one, kind of your choice. And it's okay if you do end up with a 0. If that's the frequency for a class, that's okay. Now here's where we start to get a little bit different. We now have to take frequency times, and it's each midpoint squared. You square the midpoint first, then you multiply it by the frequency. So it's not just taking this column and squaring the values. It literally means we have to take frequency times the midpoint, but just the midpoint is squared. I do want to make sure I emphasize that. Just the midpoint is squared. So this column doesn't really build off of the last one. We do have to go through and actually find those individual pieces. So we can't just square that second to last column to get the last column. And again, maybe you might want to write down just a couple so when you look back, you can recall that you had to square the midpoint, then multiply by the frequency. And again, let the calculator do your busy work for you. Now, just like we saw with our variance and standard deviation formulas for ungrouped data, we look at the formula and we think, holy cow, what the heck's going on in there? But now we're starting to get a little more familiar with the symbols. So first of all, we start off with that little lowercase n. And that's just our sample size. Sample size in this case, it's your total frequency. Total frequency gets you your sample size. Inside the first set of parentheses, we have that capital sigma, so we know we need to add up a bunch of values. In the first one, we have frequency times that midpoint squared. So that comes to us from our last column. So that midpoint's being squared, so that comes to us from our last column. Minus the next set of parentheses, we see that capital sigma again, so we know we're going to have to be finding a sum, and it's frequency times midpoint, so that's our second to last column. And we add those together. There is a squared. We need that quantity squared for our frequency times midpoint. The denominator, bunch of n's going on in there. N's just our sample size, aka the sum of our frequency column there. So we just have 20. And now I realize 20 minus 1, yep, we all know that's 19. But again, for the sake of notes, for the sake of them being a resource, I would write out the 20 minus 1 just as a reminder. That's how I got the 19. What I want you to do is I want all of you to try out the computation piece. Half the battle is getting these set up, getting the right values in the right place in the formula. The other half of the battle is doing the correct computation. So just take a minute here, take a little pause here, and see if you can get the correct values. You should be roughly coming up with 82.0. Now, I know I usually get the question, Miss Golly, do I have to have the 0.0? Yeah, you do need the 0.0, guys. You need to go one more decimal place in the data itself. Standard deviation, just the square root of your variance is all we're going for. Remember, guys, rounding rule. I know we talked about it yesterday. We've talked about it today again. Rounding rule. Go one more decimal place value than the actual data itself. So our actual data values, they're whole numbers. They're the ones place value. So I need to go to the nearest tenths. That's why I have the 82.0, because I did round. Now, if it worked out to be exactly 82, perfect, I didn't have to round, I can just put 82, that's okay. But if I have to round, I need to go one more decimal place value than the data itself. And that's just because I had to round, okay? Sometimes it happens, our next measure, variation, sometimes it just so happens that you have two different standard deviations that you'd like to compare, but the units of the data you're trying to compare are different. So if you're trying to compare two standard deviations and you have different units, we use what's called the coefficient of variation. If you notice, the formula is the same, sample versus population. The only thing that's different are the actual variables we have in there. For either one, you're taking your standard deviation divided by your mean, and you're multiplying by 100. So this will, in fact, actually give us a percent. So the higher the percent, the more variable your data. The more spread out those data values would be from their mean. The lower the percent, the less variable the data, the less spread out those data values are from their mean. So the closer the data values are to the mean, the lower your percent will be. So just one quick little example of this, just so you get an idea of what I mean by the units being different and what types of numbers or values we're going to get from this. We have the mean number of sales of appliances over a 6-month period was 110. Standard deviation was 7. The mean commission was $5,875 with a standard deviation of $830. If I wanted to actually compare the variations of the two, right now you're comparing apples and oranges. We have the number of appliances and we have dollars. So I can't really compare them very well until I get them to be similar unit-wise. So in order to do that, for the appliances, CVAR, we have our standard deviation divided by our mean times 100, and that roughly comes out to be 6.4. Again, we're looking at a percent. Do the same thing for the commissions. And we get roughly 14.1%. So again, now I can actually compare the variation of the two data sets. The higher the percent, the more variable the data is, the more spread out the data is from the mean, The smaller the percent, the less variable the data, the less the data values are spread out from the mean. So in this case, we can say that the appliance sales, that data set's less variable than our commission sales. I wouldn't be able to tell that just purely looking at the numbers from the set. I couldn't do that because the two units are different. We have number of appliances versus dollars for commission. So it's different units. Next level of variation, the range rule of thumb. I do need to stress this for you. It's a very rough estimate of the standard deviation. Usually as soon as I show this formula, people are like, sweet, done. I don't need to make those tables. I don't need all those sigmas and mu's and all that stuff. I can just do the range divided by 4. Well, it is a very rough estimate, and it should only be used when the distribution's unimodal, so it only has one mode, and the distribution's roughly symmetric. It's the only time this should actually be used. And again, it's a rough estimate. If this would give us a good enough estimate, we just use that all the time. You can use it to estimate smallest and lowest, or largest and smallest data values. You can take your mean minus 2 standard deviations. That should roughly be your smallest data value. Your largest data value would be your mean plus 2 standard deviations. And again, these are estimates. They're actually very rough estimates. Here we go. Going to finish up with one theorem and one rule. Chebyshev's theorem. Chebyshev's theorem. What this theorem says, the proportion of values from a data set that will be within, it says k standard deviations of the mean, will be at least, and we have a little formula there, 1 minus 1 over k squared. The k, we can fill in with a whole number, and that will give us, again, the rough proportion of values that should be within that many standard deviations. This will apply to any distribution regardless of shape. So here's what this formula is saying. If I want to know roughly how many data values or the proportion of values that should be within 2 standard deviations of my mean, I would put a 2 in for my k. So we're putting it in for k in that little formula we started with. If I put a 2 in for the k, do a little bit of computation, I come up with 3/4. So 3/4, or 75% of your data values, should fall within 2 standard deviations. Now sometimes people struggle with, what do you mean within 2 standard deviations? So I have that little graphic down there for you. Within 2 standard deviations means I have my mean at the middle of my distribution. If I add 2 times my standard deviation to the mean, and I subtract 2 times my standard deviation from the mean, the values that result, 75% of my data values should fall within those 2 values I get by adding 2 standard deviations and subtracting 2. We can do the same thing with 3. You could keep going and do 4 if you'd like. The numbers are just going to keep getting bigger, closer and closer to 100. So if we put a 3 in, we do a little bit of math, a little bit of computation, and we get roughly 89% of data values will fall within 3 standard deviations. So again, that means if I add 3 standard deviations to my mean, I subtract 3 standard deviations from my mean, the values that result Roughly 89% of my data values will fall between those two. It's just giving you an idea of the distribution itself. How many data values should roughly be where? What percent is happening there? That's what this theorem talks about. Then our final rule. It's called the empirical, aka normal rule. This one, however, only applies when the distribution is bell-shaped, aka normal. The normal distribution, we'll hear quite a bit about that. We will in upcoming units. What the normal rule says, roughly if your distribution is bell-shaped, and you'll see a bell-shaped distribution down at the bottom, roughly 68% of data values will be within one standard deviation of your mean. 95% will fall within 2. 99.7 will fall within 3. So again, this is very specific. It has to be a bell-shaped, aka normal distribution for this to happen. And again, this is a rule. The last one was a theory. So just kind of taking that as they are for those. Okay, so again, the last one in theory, this one's more of a rule, but it only applies to your normal distributions, your bell-shaped ones. What I want to do, guys, is finish up. I know we did a lot of computation types today. A lot of having to make a table, and some of the stuff can be kind of tedious, kind of time-consuming. So let me help you out a little bit. Take your calculator. Enter the chicken sandwich data into list 1 for me. Enter the chicken sandwich data into list 1 for me. Once you have your data entered in, go back to the stat menu, arrow over to calc. Option number 1 is going to be amazing, hopefully for all of you. I'm hoping. Choose option 1. Now your calculator screen might look different than mine. This is one of the newer operating systems. So if you have one of the newer systems, if your screen looks like mine, make sure L1 is your list. Arrow down and you'll hit calculate. If you have one of the older calculators, you will need to type second 1 to get L1 on your screen, and then press enter. Let me just show you everything that the calculator just did for you by you simply entering in the list and going to this one feature. The very first thing, if you notice, X bar. X bar is none other than our mean. Our sigma with X. That means the calculator took all those data values and added them together for you. Our sigma X squared. It took all those values, squared them, and added them together for you. SX. Holy cow, there's our sample standard deviation. There's our population standard deviation. There's our sample size. Arrow down. Minimum value, median, maximum value. All very, very handy things. And in case you weren't paying attention, I just told you that just gave you the standard deviation. This gave you the standard deviation. Now, I always get the question, so Miss Galley, like on a test, and you ask me for standard deviation, can I just do it in my calculator like this? The answer is yes. You absolutely can. Here's the catch, though. You have to know where to go on your calculator to get it to do it. I am of no help on calculators on the test. Zero help. I want to make sure I'm very clear on that day 1 with the calculators. You also have to know then what the symbols mean. So it can't just be, okay, Miss Galley got this whole list. Now, which one's my standard deviation again? I will not answer that on a test. Homework, assignments, absolutely, I'll answer anything you want. But you have to know how to do it on the test.
So which one's standard?
What your calculator gives you with this is for ungrouped data. We also had grouped data that the calculator will do, but we don't have time to go through today. So if you want to know what these things mean, how to find them, please look at pages 161 and 162 in your textbook. All the steps are outlined. This textbook does a great job giving you the technology steps. Does a great job. So that's where you can find your extra resources.